screen as well. Screen 1. Great. The buffers are 7, 8. Whatever. I can wing this. Okay, great. We can finally start. Welcome everyone to a presentation on like why reflective design matters. The first question is, excuse me, how do I go down a page? Thank you. What is reflective programming? It is the ability of some type of process or program to reflect on itself. It's the ability of a language to inspect upon itself. This means that, in essence, the programmer has access to the underlying machinery of the programming language, because you need to be able to use that in order to reflect in the first place. So that's like roughly what it is at a very high level. It's just a way for a language to talk about itself, and there's a series of trade-offs. Right, it allows users to tailor the language to their needs, because while they can reflect on the language itself, they can actually customize it. Right, there is some type of API to changing how the language works and how the compiler works. It allows you also extensions to the language, because while if your default mechanisms don't work for you, well, just change them. And you can also create tools over the language rather than fixing the tools in your compiler. Like I say, want to build a build system or a doc system, you can build that external to it, just using the primitives of the language itself without having to take it in to the language and make your compiler much bigger. This has some downsides though. You need to actually design the introspection, and it requires open design, right? You can't be afraid of opening up some of your internals and while documenting them, and you do need to design them. It's no longer carefree where you can do whatever. So the first trait I want to talk about is, so I want to get into like the common traits that all these languages kind of share, right? These are family of languages like Common Lisp, Factor, Erlang, and Smalltalk. Yes? Oh yeah, sorry. Is this better? Yes. Perfect. So there's a couple of traits which are common to all of them. The parser is trivial, and the parser itself is an extensible API. What do I mean by this? If you look at any Lisp or Factor system, the parser is this: you read. You just call the read function, and it reads a character or a word. For example, for Factor, it just reads a word, and then another word is separated. So, for example, if I open up my Factor REPL here and I increase the font because this is horribly small. Here you go. So a word would just be like this. It would be like plus here. It would be it's any symbol really. Even this is an effective plus map. Even this is I read a symbol from it. I read a word. It sees that it's this character. And from this is called a reader macro. This controls what's read afterwards. Then the reader reads again, and then the code gets executed. Right? The reading is trivial. It's just reading some words and executing some code. And this is open to the user. You can extend this and make your own little funky symbols that do their own thing, because the API is you have a lexer, and well, you can just read words off of it. Further, since the syntax is simple, these languages tend to be homoiconic, which means that you can write functions over the syntax itself, meaning that you can extend it upwards. So this is one part of reflection. This is a reflection that even Scheme exhibits, which is you can reflect on the syntax. This is not enough for reflective design, but this is just a common element between languages which have reflective design. So this is, I think, a rather key and important feature, is just the ability to have like an API into the reader itself. This is in contrast to a batch language. In a traditional batch language, the syntax is a lot hairier. You can't implement the parser trivially in, say, your C program, right? So if you're trying to implement it inside your virtual machine itself, that requires a lot more lines of code. It's a lot more bug-ridden. The user can't extend it. It's just much harder, right? You end up with Baroque macros, kind of like what you have in Rust or C, or you can name any language really, and it just makes doing any of these extensions at the syntactical level hard. But syntactical extension is not the only thing that we can do. So here's the entire syntax of Pharo. This fits on a postcard, and it's really neat. This is the entire syntax. This is complicated syntax. I would say this is complicated, but this is everything in the Smalltalk programming language. Just wanted to kind of show that off because that was cool. Yeah, I actually want to get to the second. Yeah, reflective compiler. Yeah, so that's one part of being reflective. The other part is a compiler being reflective upon itself, or rather reflections in reflections. So what this means is that instead of viewing your compiler as a process where you take your program, you compile it to a binary, and you ship the binary, you kind of view your language as an environment. And instead of it just being a binary, you have functions to hook into the environment and reason about it. So you have meta reasoning and metacognition. And this is something Scheme often does not have. And this is what Scheme kind of fails from a reflective point of view, but languages like Smalltalk do quite well. That's why, for example, we can make tools like this. I didn't launch this before, so let me just launch this. I can make tools like this. So here we have an inspector. So I have some playground here. 1 second, find my playground. Sorry for the spec being really small. It says integer. So this looks up the plus function in the integer slot. I can inspect this, and I can see, for example, the source code. The source code is saved right here, plus number. There's some logic. We can see the bytecode. So this is the bytecode that gets executed. This may or not be interesting, depending if your application requires high performance. You would actually care about this. You can see the IR of the compiler. This is just what the compiler produces itself, right? It has all the labels and basically the graph for it, and you have some AST and how it parsed it. All this information is available along with breakpoints and metadata, and you can also have things like, for example, the tooling here, where I can look at this. All this is within the language because the package system is open, and I can search all of this. So there's a bunch of tools made on this that allows me to store data in this, write data to this, reflect on it, even make graphs. Like if I show you here, if we're doing dependency management, we can see the baseline graph here. There was a more interesting one that I had earlier. I apologize. I think it was under Pharo self, baseline of Pharo. Go to this. And you can see here, this is the dependency graph. And this is live stored within the programming language. And you can click on this and see what your big dependencies are. Like this one was a general tests, which is a very big one because it tests the entire system. But the point of reflective design is that you have access to this. And this is a common theme. I can show it to you in another programming language, Common Lisp. Yeah.
Playground. Can I edit the definition of integer?
Yes.
And
yes.
When I do,
yes.
will everything that's using that, which probably includes almost everything, just get all fucked up?
Yes. I've done it. For example, you can write false become true and crash your system. Not in Pharo technically, but you can in a lot of things. So yeah, you can put breakpoints if you want, but yeah. You can do anything because the system's live. Even in Common Lisp here, that's more text-based because you can see this. I have access to everything. You can write, say, a proof assistant on this. Here, I'm looking at the current package. I'm able to see the present symbols, the internal symbols, and the inherited symbols. All this doesn't matter. The important part is that all this information is live and we can deal with it. A language like Factor does this with documentation much better. I think, where did I put my Factor? I put it on here. We have like stuff like here. Like I was going to show you dump basic if. This tooling is really nice in that it like shows me the compiler, and I can even edit this live. Where if I change this definition, it'll show me live, and I can even change the compiler here, which is running optimize CFG. I can just change the compiler path itself, and then I can see what the graph changes in live time. There's very low barrier to entry for people committing to the compiler and committing the libraries to the compiler because this is within the language itself. It's also another important property. Most of your compiler moves from the host language, from the language which you wrote the compiler in, to the host language itself, right? You write some dumb compiler interpreter and then you self-host, and then you can do this in your very own programming language. It's not actually very complicated. This entire code only has 11,000 lines of C++, and everything else is Factor, right? Hundreds of thousands of lines of Factor, only 11K lines of C++, which is like nothing. So I would argue that's a very important thing. I would compare this to a batch language. And a batch language, you have very little introspection, right? So this is showing the data heap. So you can actually click on all these. It's really neat. This is some documentation, and this is just some code I wrote, and this is that code. But in a batch programming language, you have the issue of you run your code, and then suddenly if a bug were to happen, an error were to happen,
suddenly everything just breaks. You have to maybe go through some broke logs and like check some file and temp, and hopefully your answers get printed there. Whereas compare that to Smalltalk, where I run all my tests, it gets saved in a backtrace, which is live. I can edit code in the context of the backtrace as if all the data was live, evaluate every expression there, even store state, dump state. I think it's orders of magnitude less work to work in a system like this that just allows me to like look at this data and write tools for myself. I can write static analysis tools like Proof Assistant, CACL2 for that. One of the last point that I want to show people is meta objects, or how do I satisfy all my clients' needs? And this is a cute little graph of the Smalltalk inheritance system. And I want to talk about the meta object protocol. I think this is another point of environmental reflection that I think gets little attention. I would argue the MOP is really great. So something that is amazing is, so say we have an object system, we call it the common Lisp object system, for example. You have great things like fields and methods, right? And fields are stored with the allocation. So when you allocate a class, fields are stored with it, much like an ML type, right? From writing a struct in C, you can see how many bytes gets allocated. Some issues may arise in your business use case of, well, what if all these fields aren't real? So what if I'm allocating hundreds of fields within some type in some God object or something? And, that really hurts our allocation because we're now reserving hundreds of megabytes or maybe hundreds of kilobytes, which destroy L1 cache. When in reality, we can store this in a much more sparse way. With the meta object protocol, you get to decide how allocation works. You can say, well, gee, I want to allocate this in a virtual table. So instead of storing it with the thing itself, you can customize how your objects work to be stored in some class somewhere or some fee table that escapes garbage collection or doesn't escape garbage collection. You can do things like, for example, Commons does not have a good serialization situation with default classes, right? I cannot just dump my classes to disk and have it persist across the network in a stable way like you may want in a blockchain. However, there has been work by this lady named Haley, who made a meta class for Common Lisp objects that allows objects to persist, right? They actually get saved in a format which is applicable to send over the network. I don't know the exact details, but you can use the meta object protocol to kind of change how behaviors of any object works. You can just do that. It's not very complicated. It takes an issue with design is that it takes a lot of design, but you get really good behavior because if your data structures can't cut it for the user, they're going to find ways of hacking around it, right? They're going to allocate some data in C. I know there's a big thing in OCaml where Jane Street uses C and uses OCaml, but they allocate a value in C so they can avoid the OCaml garbage collection. With Meta Object Protocol, you can do that for free without making Baroque code that you have to worry about and have a maintenance liability issue. So, I think the Meta Object Protocol is great. If you compare it to a batch compiler, like OCaml, if the default trade-offs do not fit your business needs, I'm sorry, you have to go around the language, you have to go around the compiler to write Baroque code. If the resolution mechanisms don't work, well, sorry, don't do it. Another example is you can actually do kind dispatch on Common Lisp if you change how the meta object works. You can dispatch on the class itself, and that is, for XAML folks here, dispatching on the kind of a thing rather than the type. So you can imagine type classes for kinds, so kind classes. And you can do that with Meta Object Protocol. You can just bake in your own resolution system. Great. You can even debug them live because it's, again, the compiler is open. And so, I think there's a really big contrast in how we can model data when the compiler is open and we can make business trade-offs, like, trade-offs for our use cases. So I just want to kind of get down to the final points. A reflective language usually has open syntax of some kind. It doesn't have to be. Smalltalk doesn't. It has a reflective compiler for sure, because you need environmental reflection to extend your help, especially if you don't have normal syntactical extension, and you have some way of changing how your objects work, because your work may be performance critical, or it may have weird properties, like you want to serialize things over the network and have it be the same across instances and across machines. You can do all of that with open design, unlike batch design. And I guess one final takeaway is that it makes it easy for you to get into a system and learn it. The system kind of encourages you to learn it as there's tools inside of it to help get acquainted with it more. The rules around your language are trivial, or much easier, sorry, because there's not so many special cases all over the place. You don't have sugar over here. You don't have like special resolution over here that, oh God, how does Scala dispatch on this thing? Like, how does it, know what to dispatch on? You can just inspect and see what the resolution would be for any particular type. You can see where it comes from. You can see what extensions call it. All those rules are rather straightforward. Any issue you may have, like deployment and all that, is debuggable. Suddenly, you don't have this issue where when you're building big monolithic applications, like Mata, for example, you may have tests which are very, very hard to debug and take a very long time and have to recompile. Instead, you can leverage your language in order to make it more friendly for the engineers working on it. You can just dump logs, you can keep context open, you can keep evaluations open. I can just dump the value of the things that I expect rather than having to waste hours of my life not doing that. And you can use the language more naturally, again, allocation and all that. And your language is extensible to whatever problem domain you may want, say like proof assistance. And that's really it for like, I guess, reflective design. There's a lot more points I didn't include, like meta-circularity and all that. We can discuss that after, or you can ask me questions now on whatever. So, yeah. Yes, Isaac.
So it seems like it would be awfully hard to prove properties of data structures if the rules of if the say methods of the object of the structure change after I built it.
It's not as bad as you think. So yeah, if you change the structure, that would invalidate your proof, for example. However, you would have tools in order to deal with that. For example, there are tools in which you can add like extra checks, and you can have it if the types are, say, different, error and not be committed to your system. For example, the language Unison does not commit changes which are, say, inconsistent to the database. So I would argue that you could add more tools around that. Like I don't think that's any harder than it would be in, like, say, Coq or Agda or anything else or any other proof language, because I'm just giving you a mechanism to change some things which may actually help you rather than just arbitrarily cutting it off.
I have one question which is relevant to that, and then one question which is not relevant to that. So I'll ask the relevant one first. So it seems like there are kind of three dimensions of language design that are being touched upon here. One is syntactical simplicity, or maybe called mechanicity. One is reflective design, the ability of the language to reflect on itself. And another one is formal reasoning, or the ability to, like, let's say, isolate complexity of different parts of your system by proving simple properties about the behavior of those parts. Are there any fundamental trade-offs between these dimensions, or can you, like, have all of them at once?
I believe you can have all of them at once. So the first two I've shown, like, for example, Common Lisp has the first two, and there's a subset called ACL which has the third. Things that you do have to look out for is that you have to design for hackability. I would say you should probably design to have your type system be pluggable. Common Lisp has this. But I think it is...
Why?
Because you may want users to write extensions or write...
What do you mean by pluggable? Like optional? Like...
No, it's not necessarily optional. It's the user can extend...
Independent of the syntax?
Yeah, well, syntax doesn't matter. Like, syntax isn't really real on things. Like, you can just... Like,
but I just... What do you mean by pluggable?
I mean pluggable, like, you can extend it or change some aspect of it. Right. And for example, ACL2 is an example of this. It doesn't change the Common Lisp type system per se, but it does, like, say, add another dimensionality of safety to the language and the environment.
For me, a type system is like a series of type derivation rules. So when you say pluggable, do you mean that the user can, like, introspect on and modify those rules, something like this?
They could if they wanted. So say if you wanted to upgrade your type system, you could. I think, for example, you'd want a protocol, though, of communication. For example, so one very successful thing in all the things that I was talking about is that they all had interfaces to each component. When I was talking about the meta object protocol, there is a very specified protocol for every aspect of it. And so I think you would similarly want to design a protocol for changing types if you wanted to, say, do that.
Extremely tiny.
Yeah, exactly. So your base protocol is extremely tiny, and I believe Hoon has a lot of these properties. Does it not, Ray?
Yeah, we have all of these except the syntactic one actually, right, which is the easy one.
Right.
Just
We just not efficient.
Yeah. So Racket has the third point that Chris mentioned, but Racket does not have environmental reflection. Racket's environment is horrible if you're really looking at it for like serious work. Yeah, Terrence?
Yeah, I wanted to mention actually, and it relates to Christopher's question, but when your language includes proof content, there is another form of reflection that becomes available, which I think a language also ought to have, which is then the language ought to reflect its own citing rules, right?
Yes.
It should reflect its own citing rules, so its own citing rules should be types of the language. And indeed, there should be a protocol for operating on those rules themselves, like having a type system which derives from the type system of the language itself, right, or modifies the type system of the language itself, right. And there is an established protocol for modifying that, known as category theory, right? Hence,
Yeah.
the use of it.
Yeah, I agree. That makes a lot of
Kind
sense.
of like the web work is being aimed at, right? It's you don't use just primitive Gab as your type system. You write a type system in Gab.
Yeah, exactly.
And the only constraint on the modularity or the upgradability of that type system is that your new one also has to be expressible in Gab,
Yes.
which is very small in general.
Exactly.
But could you, for example, require a further constraint like your new one is expressible in some previous type system which was itself expressible in Gab?
You can do that.
You could.
But I mean, the latter is still expressible in GIMP because they're all expressible in a very simple language. The huge difference, there's a crucial thing to realize, which is that their expressibility and interpretability are not only different, but they're almost opposites. They're almost duals. What it takes to express the rules of a type system, to note the rules of a type system, is as Gödel showed extremely weak. And like in practice, MetaMath, for example, shows just how weak that is. You can express the rules and check proofs of rules with immensely powerful type theories, even ones that are not full of non-computable functions, right, like ZFC, just with an extremely simple substitution-based rule system. But of course, interpretation is completely out of the question, right? Interpreting something you can only do in two ways. That's the definition of being a strictly stronger theory, or a stronger theory that you can interpret something into another theory, right? You certainly cannot interpret ZFC, not only in MetaMath, but not even in any computable language.
Okay, that makes sense. So the second question is much more pragmatic and is it's there when you show these kinds of interfaces and discuss this kind of introspectability, there's like somewhere there's a database, right?
Yeah.
Maybe that's in memory, maybe it's partially disk. I'm curious, like, what are the requirements on that database? Has anyone tried like distributed
I
databases?
think
for
there
this
may
sort of
be.
system?
I believe there may be, and I think Hoon may be a good example. But before I mention Hoon and ask Ray, I believe yes. Like for example, there is a primitive in Smalltalk called become, where an object can become another object, and this is useful in the context of distributed computation because you can store data in the image in your database that can then be fetched on the network and become the object. So you can reify some type of state. So you can imagine that. Oh boy, you know about some namespace that someone has on the internet over here, and so you have that object become the real one after you fetch it off the internet, and so you can further browse it. So I believe you could, and I think Hoon, Ray, if you want to explain it, actually does that a bit as well with how this works.
There's a couple levels to this. There's like the permissioned level or the fully trusted level, which is like what Erlang does. A full Erlang OTP system can be extremely distributed. But, you have to deal with distributed systems problems, but not like the interesting trustless ones. The Urbit model is like a very specific, defined sort of trust, right? Where you have this sort of global namespace that you have an identity and you own everything under that identity. And you accept only what you define as well-formed messages from other parts of the network. So that's like a particularly rigid thing. And like the open problem would be doing this for like the sort of extending its sort of arbitrary trust models.
Right. Well, funny that. But I'm curious, what exactly like? Why hasn't that happened yet? would you say? Because it seems very natural to me. So if we think ANOMA might possibly solve this problem, hint, hint, but I'm just curious, like, maybe ANOMA also does a lot of other things, and maybe not all of them are necessary. So what do you think are the missing components for this specific problem, right? Like distributed reflective programming under heterogeneous trust.
Ray?
Oh no.
Oh, for it's a
yeah.
question for me. Yeah, so I think ultimately it probably comes down to accepting like what like extending your definition of well-formedness
Uh-huh.
in a way that isn't just, you know, I've defined well-formedness by Fiat, and the rest of the network can either be compatible with me or not, which relies on this sort of which relies on like out of band of the actual programming system, people accepting that generally accepting that something is well formed. So some kind of way to progress well formedness from within the system itself, right? Rather than just declaring it by Fiat. Either like in Erlang, you know, you trust everything completely, so anything can send any message. You know, in Urbit, anything can send any message, and you sit there on your single node choosing what to accept and reject. So the missing piece is like a more complex world than that. Like if you get something that you didn't know was well formed yet, but now it is well formed, and you can get like the methods to interpret it at the same time as you learn that it's now well formed. If that makes sense.
Sort of. What exactly is well formed? Define the term.
Well, for basically,
decoded?
not quite decoded. Does it type check? But type checking is kind of too weak unless you have a very powerful type system, which probably can't exist. But like, does it type check, and does it comply with the semantics, like the protocol semantics you expect?
Right. Okay. So it's a predicate basically on arbitrary user input. That
Yeah.
yes, and whatever that predicate is like the definition of well formed for this system.
Yeah, I think you probably so runtime type checking is a huge part of this in Urbit specifically. In that you run a value through the type checker. Any value you get from the network, you run through a type checker at runtime to cast it to the type you expected, and if that type check failed, it was ill-formed. And then additionally to that, like the code that's handling it is allowed to crash at any point, and if it does, then that means it was ill-formed.
Right. I think these are kind of implementation details, but I guess the other question I have is one thing, one piece of context that we sort of have from the distributed systems side is, at least if you want to operate in a model with heterogeneous trusts, you do not have one database. You have like one very heterogeneous sharded database, and you have individual views of that database. And individual views may well be consistent with each other, and you can check if they're consistent with each other, but they might not be consistent with each other. You can impose whatever rules you want, basically, on how you merge different parts of that database, and similarly, whatever rules you want. Yeah, so custom type checking or whatever, and whatever rules you want on how you interpret the subsequent state. But
and so the question for a programming system is, can you turn this into a namespace, basically?
Right. I mean, we can. I think that answer is clear. But the namespace is going to be in part segmented by what your trust model is. So if Jeremy and I share no no trusted counterparties in common, then we are going to be unable to interact, basically. We could still look at what each other think, but we would be unable to interact because there's nowhere in the system that either of us is kind of willing to run code, such as the both of us are willing to run code.
Sure, but like if you decide to form a Jeremy and Chris system that progresses according to some rules that you define at the beginning, then you can do that.
Right. Yes, this is possible. Yeah, it's interesting. I mean, I'm curious what, were you to build this sort of a system? I mean, Anoma has other things that you probably maybe you don't need, like privacy, at least not for the simple part of merging distributed history with arbitrary rule sets type systems. Is that an interesting tool? What does that look like as a tool? It's like a distributed database programming language. I don't know. Do you understand this, Thrust?
Yeah.
Sort of, because if you think about it, all languages are databases in a sense. You have the namespace that you're storing for information, and you're storing it in a database basically. So to me, I'm not really sure what you mean by a database programming language.
I mean, okay, so suppose that we have here Git, which is a protocol for merging source code changes that is basically not aware of semantics of the code which is merging. And it seems to me like what the hypothetical here being discussed is the combination of reflective design and a type system in Git, such that would be a protocol for a distributed code collaboration that is semantically aware. And that could, for example, type check. So you would be responsible for integer, and Tobias would be responsible for I don't know, what do you do with integers?
Ooh.
No. What do you do with an integer?
Addition.
Yeah, Tobias would be responsible for adding up the integers which represent something, whatever. So in this world, then you, at least in some state of the database, you control the integer type or object.
I think this already sort of exists. At least this existed in old Smalltalk systems. I believe there's an article about Smalltalk Envy in particular, in which they talk about their own Git system, where when developers make their own methods, there was responsibilities. Some people have responsibilities of the whole class, some people have responsibilities of certain methods, and inside the Envy Git control system, it's not Git. They had to make their own back then. I believe that
Envy is the control system. Yeah.
Right. But they did not have necessarily types.
Smalltalk did have types. There was a variant called Strongtalk that Gerard Butler, who later made Newspeak, did. And Newspeak has an interesting security model for say web computation in which namespaces are inconsistent, for example. So yes, there was a thing called Strongtalk that was a Smalltalk system. So yeah, it existed.
If you want to use Git as an example, there's the as you probably know, Git has plans to transition its main hash function from SHA-1, which is somewhat collision vulnerable, to SHA-256.
Right.
The way this has actually been implemented in practice is just it's sort of the wrong way, in the same way IPv6 was done the wrong way in this totally separate format. A SHA-1 repository cannot interact in any way with a SHA-256 repository. The only way you can upgrade it is to destructively convert your whole thing. So if you had a more general protocol here, you would simply just you would extend your hash type to be your hash format was formerly a SHA-1 hash, 40 bytes or however long they are, and now it's a SHA-256 hash or a SHA-1 hash. And you just add the constraint that a SHA-256 objects can reference SHA-1 objects, but not the other way around. And then you could then you would have a very easy, non-destructive upgrade path for everyone.
Right. We should actually bookmark this specific thing, because the one security assumption we make in Anoma that is absolutely unavoidable is hash functions. And we probably want the ability to upgrade them in the future without destroying everything. Anyway.
Yeah. Right. Yes. Marisi.
This is more, but what is your strongest robot use case for the sort of language?
Can you say that one more time? Sorry.
What is the strongest robot use case? For the sort of
Real
language?
because
And can you repeat the question, please?
okay. So Marisi asked, what is the strongest real world use case of the system?
Yes.
I would say so. I'd say maybe Erlang. Erlang is a system which has to have extremely high uptime. For example, I believe in the paper that we read, at most you can have at most 2 hours of downtime in 40 years. I believe that was what was said in chapter 1 and 2 of Joe Armstrong's thesis. And there's over 1.7 million lines of Erlang being ran in the 90s, probably the biggest functional programming system to date, except maybe Jane Street these days. And I would say Erlang because you have hot code reloading, you have fault tolerance. If a process dies, well, it doesn't interact with any other process, and they exhibit some reflective design, mainly on kind of the environment and process side. They don't have all the reflective design, but they have some strong ones for running multiple applications within the same system and for pretty good fault tolerance and keeping all those things alive in one image, essentially.
Yeah, there are running Erlang images out there that have been up for decades that you can just go in and get a shell on and hot debug if you have to.
And then
They
there's
just-
other systems.
For decades at a time.
Yeah, and there's other systems that we don't know about. Like I know French nuclear power plants use Lisp machines because they're taking like a whole big stack of Lisp machine books out of French nuclear power plants. So I'd say these systems are used in a lot of places that we don't expect as
I
well.
mean, the French nuclear state doesn't have a type system. It's a bit terrifying.
Not necessarily the case, but yes.
Yes, as a
This kind of self-reflective eval situation sounds like it would be highly amenable to a Fujimura compiler.
so what kind of time?
Fujimura compiler.
Can you say them?
Fujimura.
More comfort.
Tomorrow.
Compilers of things that's there. No,
Yes.
Yes. Right.
Oh, so you mean a meta? I forget what's a metacircular evaluator?
Yes, I think so.
Oh yeah. Yep, they are. They are quite friendly with metacircular evaluators. Okay, yeah, they're quite friendly. I was actually had a slide on metacircular evaluators, but I cut it for kind of it would go on for long if I talked about every property, so I cut that one. But I think metacircular evaluation is really important in like trying to understand new things and changing semantics for like understanding things.
Well, as far as I know, it's not the way almost anything is actually evaluated these days. Maybe
3Lisp kind of is. 3Lisp is kind of dead. 3Lisp did.
Yeah, I think more important than that is just exposing all of the stuff that would be compiler internals as just functions in your standard library.
Yeah. No, go ahead.
I mean, honestly, I think urban images are a very impressive real world use case of reflective.
Yeah.
Yep. The way that you can dump an image somewhere, pick it up and drop it somewhere else and it, rejoin. It resumes networking as if it had been whatever the way things ought to be, I think. There's a cute YouTube talk called something like "The Most Beautiful Program Ever Written,"
Yes.
which is on the subject of the 5-line, Lisp solve in the circular.
It's by William Bride, I think.
Yeah, that's right.
So William Bride made Mini Canaran. He's a big fan of
Oh,
it.
you saw that? Okay,
Yeah.
I didn't realize that.
Well, I would like to thank everyone for coming here. Feel free to talk to me about languages in the future of alpha languages.
I have to stop the recording now.